Increasingly, hydrocarbon gas compression applications must deal with gas that contains hydrocarbon liquids and water. Conventional solutions to the challenges of wet gas compression require very large and heavy equipment. Now Dresser-Rand combines two technologies in one game-changing innovation. Introducing Datum ICS, the integrated compression system, centrifugal separation technology, and datum compression technology in a compact single-lift package. Building on its successful Datum multi-stage centrifugal compressor product line, Dresser-Rand worked with Curtiss-Wright EMD, a subsidiary of Curtiss-Wright Corporation, adding an electric motor to develop an integral, high-speed, close-coupled, motor-driven, zero-emissions centrifugal compressor, the Datum C. Then Dresser-Rand added its proprietary centrifugal separator technology to create the basis of the Datum ICS. Within a single casing, the Datum ICS removes entrained liquids before they enter the compression stage. The unique advantages over existing technology are evident in this look at the system's centrifugal separator. Fluid enters the compressor intake nozzle and is directed through an initial static separation zone where swirl vanes impart some centrifugal force to the fluids. This allows the bulk liquids to drain off the process gas. The remaining gas is directed through a higher intensity swirl and into a rotating drum. In contrast, conventional solutions use static walls, causing the inevitable re-entrainment of liquids. The rotating drum in the Datum ICS allows a higher percentage of liquids to be effectively removed before they enter the compression stage and adversely affect the compressor's performance, reliability, and maintenance cycle. Dresser-Rand designed the Datum ICS demonstration unit to prove the concept of separating liquids and compressing gas in a single case. On the Dresser-Rand test stand, water, oil, or a combination are injected into the gas stream. Pressures and flow rates can be varied to simulate a variety of field conditions. Viewing ports provide quick visual inspection of wet gas entering the Datum ICS unit and dry, compressed gas as it exits. During initial tests of the Datum ICS demonstration unit, at a water injection flow rate of 340 barrels per day, the inlet was heavily fogged. The clarity of the discharge viewing port shows that the separator functioned very effectively. In fact, the separation technology achieved liquids removal greater than 99.5%. Even at 680 barrels per day water injection flow rate and nearly double the liquid mass fraction, the discharge port shows the separator still functioning very effectively, with separation efficiency still greater than 99%. Compare the size and weight of Datum ICS to a conventional wet gas compression solution. You'll find a reduction in the footprint and weight of approximately 50%. When compared with conventional solutions, those reductions translate to smaller offshore platforms, smaller FPSOs, and smaller space requirements in refineries. Another benefit of the Datum ICS is the improvement in reliability obtained by removing liquids from the gas stream. Liquids foul impellers and degrade performance as more energy is required to compress wet gas. And compressing wet gas leads to more frequent and costly maintenance. This impeller shows the severe erosion damage caused by liquid carryover into the compressor. Examination of the leading edge of the impeller blade shows significant gouging. In this case, the damage has been so great that the reverse side shows where holes have formed in several areas. This type of wear greatly impacts the reliability and operability of the machine. Removing liquids from the gas stream can prevent this from happening. In this example, the cover of the impeller has been removed to better show the erosion patterns on the impeller blades. Severe gouging and cutting is apparent at the leading edge of the blades. This affects the throat area of the impeller and severely impacts the performance of the stage. Removing liquids from the flow path ensures that the compressor will operate as designed for extended periods of time. Increased reliability and smaller footprint translate into lower capital and operating expense for Arctic Circle and deep subsea applications. The ability to place a compressor closer to the floor of the seabed can also mean lower pressures and extended life for oil and gas wells. Dresser-Rand is uniquely qualified to integrate its datum compressor technology with centrifugal separator technology and control system expertise to deliver the datum ICS. Engineered, packaged, and tested as an innovative wet gas compression solution, the datum ICS offers enhanced reliability with reduced weight and footprint, resulting in lower total costs of ownership. The datum ICS integrated compression system, only from Dresser-Rand.
MAN Diesel & Turbo manufactures tailor-made intricately geared compressors, also known as multi-shaft compressors. A modular design concept can be used for these machines, and all components come with extremely good references. Up to 8 compressor stages are arranged around a gear unit in the same way as the hands of a clock. The basic principle is the same in that only one drive unit is needed to rotate them at different speeds. This compressor has 6 stages, arranged in 2 sections. Downstream of the second stage, the customer can draw off a specific volume at medium pressure. The remainder is further compressed to the desired discharge pressure by the second section consisting of stages 3 to 6. Each stage contains an impeller, and each pair of stages with the same impeller speed is arranged opposite each other. They share a pinion shaft, at the ends of which the impellers are attached. Inlet guide vanes are mounted in front of the first stage of each section, here stages 1 and 3. Their blades can be adjusted synchronously, which enables each section to be controlled individually. Each pinion shaft meshes in the bowl gear with its central teeth. The pinions have varying numbers of teeth, which gives different gear ratios depending on the particular pinion and enables optimal speeds for the 2 individual compressor stages. It's the impellers, gear unit, and bearings that largely determine the efficiency and service life of an intricately geared compressor. And with MAN Diesel & Turbo, the design of all components and the related know-how come from one source. Whether dry or humid air, refrigerant, nitrogen, carbon monoxide, or dioxide, the rotating impeller sucks the respective process gas through the inlet guide vane unit. Centrifugal force works here in the same way as with a roundabout and accelerates the gas radially in the blade channels, that is to say from inside to outside. This provides the gas with kinetic energy, which is transformed into pressure energy in the impeller and diffuser. The volute then collects the gas. With each compression, the gas temperature rises. This in turn somewhat reduces the density and increases the volume. Because this means that the following compression process would then require more energy, the gas flows after each stage through piping to an intercooler that reduces the gas temperature before the gas enters the next stage. The shown process, axial flow to the stage, compression, and transfer to the intercooler, repeats itself stage by stage. This raises the pressure incrementally. Depending on the unit size, it can compress up to 350,000 cubic meters per hour to a discharge pressure of maximum 250 bar. Integrally geared compressors have significantly higher efficiency levels compared to multi-stage single-shaft compressors with the same operating speed. They can not only be used on their own. The one shown here, driven by a steam turbine and supplied with pre-compressed air by a main air compressor, is used particularly in air separation plants. They generate large volumes of oxygen, for instance for coal to liquid plants. Beside the intricately geared compressor, MAN Diesel & Turbo can supply process piping and process gas coolers, the complete train oil system, or as well the complete machine train from perfectly coordinated components. The Berlin site has developed and built intricately geared compressors since 1977, Worldwide, hundreds of units reliably compress a huge variety of processed gases daily at high efficiency levels and discharge pressures. Their modular construction principle enables them to be designed and supplied for the most varied customer processes.
Nuovo Pignone started designing and manufacturing centrifugal compressors in the early 1960s, quickly achieving a leading role and becoming internationally recognized in the area of centrifugal compressors. In order to more easily recognize the various types of Nuovo Pignone centrifugal compressors, it is important to understand the basic function of a centrifugal compressor. In a centrifugal compressor, a continuous flow of fluid increases its pressure by means of energy given by impellers arranged on a rotating shaft. This type of machine is composed of an outer casing, which contains the diaphragms and a rotor. The rotor draws gas from the suction nozzle through the impellers, across the diaphragms to the discharge nozzle located on the opposite end of the compressor. The major components of a centrifugal compressor can be divided into two functional areas. The first functional area includes the stationary components consisting of the casing, the inlet and discharge nozzles, the inlet and discharge volutes, the inlet, intermediate, and discharge diaphragm sections, the shaft end seals, the journal bearings, and the thrust bearing. The second functional area includes the rotating components consisting of the impellers, the shaft, the balance drum, the spacers, the seal sleeves, the thrust collar, and the locking rings. Gas flow enters the inlet volute of the compressor through the suction nozzle. The volute ensures uniform distribution of the gas around the eye of the impeller. In the volute, directly opposite the suction nozzle, is a fin that reduces gas turbulence and prevents recirculation within the volute itself. From the inlet volute, the gas is then drawn into the eye of the impeller and is discharged radially at a higher pressure, temperature, and velocity from the tip of the impeller. The impeller contains blades that convert the mechanical energy of the shaft into gas energy. This energy can be measured in terms of pressure, temperature, and velocity. The high-velocity gas flows from the impeller into the stationary components downstream, whose surface defines a diffuser. In the diffuser, part of the gas velocity is reduced. Following the diffuser is a return channel that brings the gas to the eye of the next impeller. Upon leaving the last diffuser, the gas flows into the discharge volute and is directed toward the discharge nozzle. The discharge volute contains a fin, similar to the fin in the inlet volute, that reduces gas turbulence and prevents the gas from continuing to flow around the volute. The increased energy in a gas is defined by the characteristics of pressure, temperature, and velocity. These three characteristics are used to determine a quantity known as enthalpy. Enthalpy depends only on the condition of the fluid and measurement of the energy content of the gas. Thermodynamic properties of the gas can be static or total. The difference between the two is that the total condition includes the energy content generated by gas velocity. Thermodynamics includes the concepts and laws describing the conversion of energy from one form to another, and the study of how these forms of energy interrelate. The assembly of the rotor begins with the installation of the sleeves to the area of the shaft where the oil seals will make contact. Next, the locking ring is threaded onto the shaft at the balance drum end. Then, the balance drum is installed and shrink-fitted on the shaft against the locking ring using double keys. Finally, the discharge impeller is installed and shrink-fitted on the shaft against the balance drum using double keys. Then the partial assembly is dynamically balanced. After the partially assembled rotor has been balanced, a spacer is installed, the next impeller is added, and both are heat shrink fitted to the shaft. Then the rotor assembly is balanced again. The sequence of balancing the rotor, installing the spacer, and adding the impellers is repeated until the suction impeller, spacer, and locking ring are installed and balanced as defined by the customer requirements. Generally, the thrust collar is added last. It is hydraulically expanded and pressed into position on the end of the shaft. The assembly of a BCL compressor begins with the insertion of the diaphragms into the counter casing. Because both the counter casing and diaphragms are horizontally split, each half of the counter casing receives the diaphragm halves. Each half is lowered into place and positioned axially by the counter casing shoulder. The diaphragms in the upper half of the counter casing are locked in place using cap screws so they do not fall out when the upper half of the counter casing is placed on the lower half. After the diaphragm halves have been mounted into the counter casing and placed in position, the labyrinth seals are installed in the diaphragm sections. The labyrinth seal segments for the impeller eye and foot are rolled into L grooves in each of the diaphragms. The labyrinth seals in the upper half of the counter casing are locked in place using cap screws so they do not fall out when the upper half of the counter casing is placed on the lower half. The rotor assembly is inserted on the lower half diaphragms and rests on the lower half labyrinth seals. Then the axial position of the rotor is set and recorded. Next, the upper half of the counter casing is placed on top of the installed rotor and lower counter casing half. Before closing the counter casing halves together, O-ring segments, coated with lubricating grease, are fitted into position on the middle split plane of the lower diaphragm to minimize leakage between compression stages. Great care must be taken to ensure a perfect fit between the two halves to avoid internal damage to the rotor and diaphragm.
Atlas Copco multi-stage centrifugal compressors use integral gear technology, the industry's most compact and efficient turbocompressor design. Our integrally geared compressors are reliable, energy efficient, and specifically optimized to your process requirements. Integrally geared compressors deliver multiple speed capability by placing rotors on separate pinions. Each compression stage runs at the optimum speed for high efficiency. Compressor bearings and gears are lubricated by the main lube oil pump, which is driven through the bull gear for reliable oil flow. The compression process begins with gas entering through adjustable inlet guide vanes, or IGVs, which are standard on all Atlas Copco compressors. IGVs control how much flow is sent into the machine, providing accurate process control. With IGVs, compressor efficiency can be increased by around 9% versus other inlet assemblies. Our impellers, available in open or closed configurations, impart kinetic energy to the gas. This is turned into pressure in the diffuser and then the volute. Gas temperature rises during the compression process. To improve compression efficiency, interstage cooling can be easily accommodated between any of the compressor stages. Atlas Copco offers a range of intercoolers that are precisely matched to process requirements and meet all relevant international standards. In the configuration shown, water coolers are available in either water in the shell, gas in the tube, or gas in the shell, water in the tube designs. High-speed rotors are supported by radial tilting pad bearings that eliminate virtually all vibration while providing superior rotor stability and smooth rotation. Depending on the application, this can be a combination of radial and thrust bearings. The bull gear shaft rotates on multi-lobe sleeve bearings. Compressor sealing options may include dry gas seals, floating carbon ring seals, and labyrinth seals in various combinations and arrangements. Our range of integrally geared compressors is used in a variety of industries, and our compressors can be customized for a specific process. As the name suggests, all compressor stages of integrally geared compressors are mounted on one gearbox. Thanks to their rotor and aerodynamic design, along with intercooling capability, integrally geared compressors are more efficient than other rotary compressors. To enhance performance, a number of other features are available, such as variable diffuser guide vanes, or DGVs, which can be added to complement impeller aerodynamics. Adjustable DGVs enable larger turndown, which ultimately results in wider process control without impairing efficiency, an ideal mix that is increasingly required by process designers. Both variable inlet and diffuser guide vanes provide stable compressor operation over a wide range of conditions at a constant discharge pressure. To control gas temperatures during compression, in situations where cooling water is not easily accessible, an air-cooled version of our compressor is available. For applications where process gas leakage is restricted, or when process gas needs to remain within the system, our integrally geared compressors can be built with dynamic dry gas seals. These seals can be supplied in single, double, or tandem arrangements, depending on the application. In fact, Atlas Copco was the first compressor manufacturer to implement dry gas seals on integrally geared compressors. Packing efficiency, high machine availability, and superb process control onto a small footprint, Atlas Copco integrally geared compressors give your process the extra edge in a variety of applications across many industries.
For over 50 years, F.S. Elliott's oil-free centrifugal air and gas compressors have led the industry with a technologically advanced design that delivers reliable, trouble-free operation with the lowest cost of ownership, offering a horsepower range of 250 to 5,000 with up to 4 stages of compression. Our compressors are ideally suited to a broad range of industries. Every aspect of your compressor's performance is governed by our multifaceted Regulus control system. This easy-to-use central control system features the most powerful processors in the industry and can be used either remotely or at the site of the unit itself. With the unprecedented control provided by the Regulus system, a manager can operate one or more compressors at a time while simultaneously achieving the greatest energy-saving efficiency possible. Before entering the first compression stage in a multi-stage configuration, ambient air or gas must pass through F.S. Elliott's high-efficiency filtration system. From there, an inlet guide vane automatically adjusts itself to changes in system demand, regulating the incoming low-velocity air or gas stream as it flows toward the first stage impeller with a pre-swirl effect. As the low-velocity air or gas stream flows into the first stage stainless steel impeller at the inducer, centrifugal force directs its flow to the trailing edge. From there, the accelerated air or gas stream flows from the first stage impeller to a radial diffuser, which converts the air's high velocity into static pressure before the heated air enters the scroll casing. To ensure perfect aerodynamics, F.S. Elliott will custom design both the backward-leaning impeller and radial diffuser for your specific application. With each stage of compression, the air or gas temperature rises, pressure increases, and volume decreases. In addition to the impellers and radial diffusers, the rotor assembly consists of a pinion supported by 2 self-centering tilting or flexure pad journal bearings. Shaft seals on the impellers prevent gearbox oil from contaminating the compression chamber. Powered by a high-speed motor, the pinions and central bowl gear are machined to AGMA quality Class 13. After passing into the scroll casing, the heated air or gas flows through the inner stage piping into the first stage intercooler, causing the moisture to condensate and separate from the lower velocity cooled air. Because FS Elliott intercoolers feature straight-through tubes, cleaning is possible, rather than costly replacement. As the air travels through the corrosion-resistant plenum, the separated condensate is removed from the compressor through a drain valve located at the bottom of the intercooler enclosure. By regulating the discharge of condensate, the drain valve increases the efficiency of the process by preventing unnecessary compressed air loss. Once the condensate is removed, the cooled air exits the intercooler and flows into the inlet duct for the next stage of compression, during which the entire process is repeated. The compressed air or gas then moves to the aftercooler, where it's cooled and any remaining moisture is removed. This highly energy-efficient process concludes with the delivery of ISO 8573-1 Class 0 certified oil-free air, ready to power a variety of industrial applications. Depending on the number of stages within the configuration, discharge pressure can reach a maximum of 350 psi-G or 23 bar-G. Whether your application calls for a hard-working industrial compressor package or an engineered custom design, you can count on FS Elliott to deliver efficient, energy-saving performance, ease of operation, and rugged reliability.
In large manufacturing facilities and process industries, Ingersoll Rand has long been a trusted partner for oil-free centrifugal air solutions. Since the introduction of our first Centac packaged centrifugal air compressor in 1968, Ingersoll Rand has been known for simplicity by design. Simplicity by design led to the reduction of moving parts and integration of major components, which quickly made Centac known as the most reliable oil-free compressor in the world. Simplicity by design also spurred industry-changing innovations, such as backward-leaning impeller vanes to improve operational range and efficiency, and carbon ring seal designs to minimize air loss. More than 40 years of simplicity by design have made Centac the most dependable, lowest operating cost centrifugal solution available, with more than 20,000 units installed worldwide. Our all-new Centac Model C1000 continues the tradition, with more than 50 design improvements to maximize reliability, efficiency, and productivity. Air enters the package through an inlet air filter. The inlet valve or inlet guide vanes regulate the air entering the compressor. At the heart of the compressor is a key Ingersoll Rand advantage, a rotating assembly consisting of the impeller mounted to a pinion gear through Ingersoll Rand's revolutionary P3 tapered polygon attachment. The attachment's precision fit and polygon shape lock the impeller and pinion together in 3 dimensions for a precise and sturdy connection. No unusual tools or pressure are needed when working on the rotating assembly, allowing for quick and easy field maintenance. Our signature backward-leaning impellers help maximize the efficiency and turndown of the C1000. Designed with leading-edge software and precision-crafted from high-grade stainless steel, the C1000 impellers are built to withstand even the harshest environments. The rotating assembly is driven by an extremely durable bull gear. This robust, precision-ground, AGMA-rated bull gear has been through-hardened to maximize life up to 25 years. It's connected to the motor via a flexible gear or dry-type, maintenance-free coupling. The low-speed bull gear bearings add to the durability, since no thrust is transferred to the bull gear shaft. The assembly rides on a thin film of oil separated from the air by non-wearing carbon ring seals, ensuring 100% oil-free ISO Class 0 air in all operating conditions, including being unloaded. Single-piece carbon ring seals minimize air loss by more than 50% when compared to labyrinth-style seals, which could save users more than 140,000 kilowatt-hours of electricity per year. C1000 self-centering flexible pad bearings provide superior dampening qualities and minimal frictional losses while delivering lower power consumption, improved stability, and longevity. After the air is accelerated by the impeller, it's slowed by a diffuser vane plate and shaped scroll, The precision-machined and corrosion-resistant vane plate minimizes turbulence and maximizes dynamic compression as the air velocity is decreased. The coolers knock moisture out of the air through temperature reduction. Water flows through the extended surface-style tubes, which effectively reduce the air temperature to as low as 5 degrees Celsius or 8 degrees Fahrenheit above the inlet water temperature. The generously sized coolers have an ultra-low pressure drop, further reducing power consumption. The resulting condensate is separated out and sent to air-saving no-loss moisture traps, maximizing efficiency. Each of 3 identical and fully interchangeable tube bundles can be easily cleaned in place from either side, making for quick and simple maintenance. The entire package is carefully managed by Ingersoll Rand's latest generation electronic controller. The controller's informative and intuitive display provides a powerful window into all vital signs of the compressor. In addition to ensuring peak performance, maintenance becomes predictive through continuous monitoring of critical components. The controller also enhances productivity and ease of use through an open web page style architecture that allows users to interact with the compressor remotely from almost anywhere. The Centak C1000 ushers in a new era in a 100-year heritage of legendary reliability, best-in-class efficiency, and maximized productivity. With industry-leading innovation, Ingersoll Rand has created a new benchmark in efficiency and reliability. The C1000 is simplicity by design, taken to a new level.
About ครับ